Welcome to this accelereyes video broadcast. Accelereyes makes Jacket, which enables MATLAB code to run fast on GPUs. Today, I want to talk about a code that was posted to the MATLAB Central forums for beam propagation methods. This post was put on the website a couple of weeks ago by Patrick Kano and is under the BSD license, and I want to under that license play with the code, and certainly the authors have put together some really cool stuff for doing beam propagation methods with CUDA. In this video we're going to talk about how Jacket can run that same code and achieve great performance benefits. So you can download the code here. This code that Patrick and his team posted runs with the MATLAB R2010B parallel computing toolbox. As many of you know, in R2010B, MATLAB released some very similar GPU capabilities, similar to what accelereyes has been releasing with Jacket for a long time, since 2007. However, in this tutorial we'll show that there's a very big difference between what's available in our 2010B with the parallel computing toolbox and what's available with Jacket, and we want to make those distinctions very clear to each of you as you decide how to best pursue GPU computing in your applications. Okay, so I've already downloaded this code and run it. It actually, if we sort of read through here, it says that this enables NVIDIA CUDA acceleration. It's a simple paraxial beam propagation method that utilizes the GPU. For smaller matrices, the standard MATLAB approach, meaning the CPU, is faster, and then at larger matrix sizes above 512 by 512 elements, the CUDA approach is more than twice as fast. So we'll show that as well as we run their code. The code actually takes quite a long time to run, a couple of hours actually, to run both the CPU and GPU versions that you download, and it does require the parallel computing toolbox. So we've already run this code. I wouldn't want you to have to sit here and wait for a couple of hours to watch the simulation run. It's actually not that exciting to watch it run. We'll just show you the results. But before we show you the results, I want to say that I was quite interested actually that there was a full application here claiming to do GPU acceleration, because really the GPU acceleration available in the parallel computing toolbox is so limited. It's really surprising that anyone was able to do anything with it. And in fact, if we look at the code, the code comes with 5 files, and it's really a good-looking code. But if you sort of search through it to find where is the GPU actually being used, it really comes down to just one single line of code, and so this is in the CUDA parax bpm.m file. You'll want to look at that in the download. But if you go to line 121 or so of that file, you'll find this one line of code here where if the CUDA switch is turned on, then you take this array free space prop and you cast it to the GPU, and you take this array E field and cast it to the GPU, and then you run some 2D FFTs and element-wise multiplication and IFFT, and then you bring it back to the CPU. So really, even though sort of the emphasis here is on GPU computing, it's really just one line of code that's running on the GPU. Everything else is just standard CPU-based MATLAB computing. I took this code and decided, okay, let's see what we could do with Jacket. And the first thing you want to do when you do GPU computing is sort of identify the large matrices, and then you want to do as much computation on those large matrices out on the GPU as possible without sort of bringing it back to the CPU. And the more work you can do on the GPU, the better performance you're going to get. So what I did is, instead of doing that one line of code, I went to sort of the higher up in the code to where those large matrices are created, and they're actually created initially with these mesh grid commands. So now with Jacket, And this is, I used the latest version of Jacket, which is actually a pre-release of Jacket 1.6, which will be available in a couple weeks. But all I did is I cast the inputs to MeshGrid to GDouble so that MeshGrid actually runs on the GPU and creates meshes on the GPU. And then I didn't have to change any other lines of code. All the way through here, everything that runs on MeshGrid runs on the GPU. These functions that I never even actually opened and looked at, they contain some operations that run on the GPU. Just by virtue of having this data be GPU data, every subsequent operation runs on the GPU. So this square root, these multiplies, all the way down this entire for loop now runs on the GPU. This large expression runs on the GPU, and so forth. I did take that. Here's that one line of code that they had before. I removed the GPU array and the gather. We don't need that anymore. In fact, this line of code is the same as this line of code, and we might as well remove that if statement. But I left it in there. And then at the very end of the file, I simply take the end result E field and cast it back to the CPU with a regular old double casting command, and that's it. So cast it, use the MeshGrid at the top to create GPU data, let all the functions just run with the Jacket optimized runtime and run out on the GPU. You don't have to change any of your code, and finally you bring it back to the CPU when you're done with it, and then we stop the timer. All of these runs of this code are going to be timed, and we stop the timer. So we're actually timing the full round-trip memory transfer whenever we're doing the timings on this file. This is a full-blown simulation. So again, this code takes some time to run, so I'm not going to run it now. I will post the code so that you can run it yourself and compare against the original CPU, and also compare against the parallel computing toolbox in R2010B if you're so inclined. I already have the results from the runs. I ran this, oh by the way, I ran this on a Tesla C2070. That's the latest and greatest, fastest GPU available from NVIDIA. It ran versus a quad-core CPU, and I'm in the Windows operating system. So I have this simple file, compare results, and we're going to compare 3 batches of results and just sort of look at the numbers on the command line in the window here. So let me just run this, compare results. Okay, so the very first thing I'm going to show is just how much faster is Jacket than the parallel computing toolbox. So here we're actually comparing GPU versus GPU. And the initial numbers here correspond to smaller matrix sizes. I believe this is a 4x4 matrix, an 8x8 matrix, 16x16, 32x32, 64x64, and so forth. I believe it, if I'm correct, it works up to 4096 at the end. So as you can see, and this code runs 2 sorts of simulations. One is constant, and I really don't even know what that means. I'm not an expert in the algorithm that's being run here. The other kind of simulation is called an update simulation. On the constant stream of simulations, you can see that for the smaller matrix sizes, Jacket's over 3 times faster than the parallel computing toolbox GPU function, ending at over 1.5 times faster at the largest matrix size. And then Jacket on the update method is a little bit, it's slower on the smaller matrix sizes, so it's only 2 times faster than the parallel computing toolbox. And then when you get to the larger matrix sizes, it's 2.5 times faster. And I would say you should really sort of discount these smaller matrix sizes. It never makes sense in any case, and I'll show this at the end. It never makes sense to use the GPU on a 4x4 matrix. It really only starts to make sense around 64x64 matrices or larger. So the take-home message here is that Jacket's roughly twice as fast if you sort of take an average of these 2 runs. It's roughly twice as fast as the parallel computing toolbox GPU functionality. All right, so let's go to now the next batch. Here I want to compare Jacket versus the CPU. So here, Jacket's actually slower than the CPU. Remember what I was saying about the smaller matrix sizes not being great for GPU computing, and indeed they're not until you get to 4x4, 8, 16, 32, 64 by 64. At 64 by 64, Jacket starts to give you an advantage. Jacket and GPUs are faster than the CPU. And you can get upwards. Jacket's getting upwards on this particular system of 3.5 times faster on this particular code. Okay, and finally, I want to show that not only is Jacket faster than the parallel computing toolbox, but it gets faster on smaller data. So with the parallel computing toolbox, you have to wait for, this was 64 by 64, 128 by 128, 256 by 256. You have to have 256 by 256 square matrices. Let's see, 4, 8, 16, 32, 64, 128. Yeah, 256 by 256 square matrices. You have to have that size matrix before you see any speed up over the CPU. So 64 by 64 is 16 times less data than the 256 by 256. So you can see that with you can solve. There's so many more problems that you can solve with Jacket because you don't have to worry about your data size being 256 by 256 or higher in order to start to see speedups. So the take-home message here is that Jacket is a mature and complete runtime. You can visit our homepage and click with, if you're curious about comparing further benchmarks with the competing alternative to Jacket. You can check it out there. Since 2007, accelereyes has been completely devoted to making GPU computing as fast as possible for our customers. And our promises is that our customers will always have the fastest in GPU computing available, and that we will, as hardware trends and programming models for GPUs change and evolve, as they surely will over the coming years, that Jacket will evolve and always provide the fastest code to our customers without you having to do anything in rewriting your code with each new wave of new technology in GPU computing. And with that, thank you for your attention.